Thanks for watching my video, and today I'm going to give a presentation on a new method for reconstructing stochastic differential equations from time series data, which is also the presentation I was giving in this year's APS meeting. So first, intrinsic noise is ubiquitous in cell dynamics. Intrinsic noise denotes intrinsic fluctuations, such as the Brownian motion or the jump process. They are quite common in key biological processes, such as cell differentiation, immune response, and adaptivity and mutation, in both single cell and population level. To be more specific, if we have a stochastic differential equation, then the intrinsic noise denotes the Brownian motion. Even with the same equation, we end up having different trajectories because almost surely, if we simulate the Brownian motion, we will get different paths. So a natural question arises as how to reconstruct or how to tell the underlying stochastic differential equation if we have a batch of trajectories as observations. Traditionally, there are statistical inference methods. They usually require an explicit model with some unknown parameters, and then they try to infer the parameters. Recently, we also have some machine learning methods like the generative modeling, Bayesian neural network, and so on. They are data-driven, which means that they don't require a specific underlying model, yet they are complicated to implement, and usually there's less interpretability because we don't know what we have learned using those methods. Given the specific task of learning the underlying stochastic differential equation from a batch of time series data, we wish to develop efficient methods for quantifying intrinsic noise in serial dynamics, that is, to reconstruct the stochastic differential equation. We hope that our method is simple to understand, interpret, and more efficient than other methods. We will apply machine learning so that we don't need a parametric form of the underlying model. However, the use of machine learning is kept minimal so that our methods can still maintain maximal interpretability. So before I go into my method, I would like to first introduce the method I'm using for uncertainty quantification for inferring the intrinsic noise as well as the machine learning tools. We are using the Washington distance to quantify uncertainty. We are using the square Washington 2 distance, which is defined as the infimum of the expectation of the squared 2 norm of y minus y hat when y and y hats obey the joint distribution pi. The joint distribution satisfies the condition such that its marginal distributions coincide with the distributions of y and y hat respectively. So basically, the Washington distance could measure the discrepancies between the distribution of y and the distribution of y hat, which are named as mu and mu hat respectively. The closer the two distributions are, the smaller the Washington distance is. So mathematically speaking, what we are going to do is to reconstruct the following pure diffusion stochastic differential equation from time series data. That is, to determine the G function f and diffusion function sigma given a batch of observations xt at different time points. We also assume that all trajectories start from the same initial condition. So what we are going to do here is that we can use two parameterized neural networks to approximate the drift and diffusion functions, respectively. That is to say, we use two neural networks, f hat and sigma hat, which takes the state variable x and the time variable t as the input, and then they try to approximate f, the drift function, and sigma, the diffusion function, respectively. In this sense, we get the approximate neural SDE model. The question is, how do we train those two neural networks such that f hat can match f well and sigma hat can match sig well? So how do we train our neural networks? We devise a new loss function which we call the temporally decoupled square Wasserstein 2 distance. By calling it decoupled, we are not looking at the Wasserstein distance between the distributions of the whole stochastic processes. Instead, we look at the Wasserstein distance between the distributions of the ground truth xt and the approximate hat xt at one specific time point t, and then we integrate over time. We proved that this loss function can be efficiently evaluated using this time discretized version. So the time discretized version can be directly calculated using the Python optimal transfer package for calculating the Wasserstein 2 distance. As an example, we consider reconstructing the Einstein-Uhlenbeck process, which is also known as enlargement dynamics. We have this underlying model with a given drift and diffusion function. With this model, we generate 100 trajectories. After generating 100 trajectories, we pretend that we don't know the drift function and we don't know the diffusion function. Our goal is to use two neural networks, f hat and sigma hat, as approximation to the drift and diffusion functions using the approximate neural SDE model. So how do we train those two neural networks? First, we generate 100 trajectories from the neural SDE model. Of course, here the neural SDE is randomly initialized. Then we calculate the temporally decoupled square W2 loss function. We perform gradient descent using the optimizer in the PyTorch package in order to optimize weights and biases in the neural networks f hat and sigma hat. We repeat step 1 and step 2 till convergence, that is till the loss function has become sufficiently small or till we have reached the maximum epoch. So the training is quite simple, just generating trajectories, and then we perform gradient descent by minimizing this temporally decoupled square W2 loss function. Here are the results. We can see that after training, the trajectories generated by our learned model match well with the ground truth model. We also made a comparison with other methods like the Wasserstein generated adversarial network, the maximum mean discrepancy, the Wasserstein 2 distance defined for the whole stochastic process. We found that our method reaches the smallest errors in the learned drift function and the learned diffusion function. Also, what is not shown here is that our method is faster and more computationally efficient than the other three methods. What are the advantages of our method? Of course, our method does not need prior distribution of latent model parameters because we directly apply neural networks to approximate the drift and diffusion function. In this sense, we also don't require the form of the model. Our method is simple and efficient to implement because we can train our neural networks by minimizing a simple loss function using the Python optimal transfer package. We don't need to implement the GAN framework or implement the Bayesian framework. Our method also outperforms some other uncertainty quantification methods like the BNN, maximum mean discrepancy, the GAN method, and so on. Finally, we found that minimizing our temporally coupled squared W2 distance could also lead to efficient reconstruction of jump diffusion processes. In this sense, we have three unknown functions: the drift function, the diffusion function, and the jump function. What we can do here is to use three parameterized neural networks to approximate the drift function, the diffusion function, and the jump function, respectively. We found that by minimizing our temporally decoupled square W2 distance, the three functions can be simultaneously trained very well. The jump diffusion processes have even wider applications than pure diffusion SDEs because they can be applied to cell division and stock price change evolution which pays dividends. Here are the references. The first one is our preprint on pure diffusion process. The second one is our recently published paper on MLST on reconstruction of the jump diffusion process. Thanks for listening.